Alrighty, welcome everyone to the Ice Giant Systems seminar series. Today we've got Tanguy Bertrand. I'll just give kind of a quick introduction and then we'll get right into it. As a heads up, we have these monthly seminars. They can be anything in the Ice Giant Systems, either system. And so if you are interested in giving a talk, please reach out to me. We're happy to kind of build up our schedule a little bit, and I'd love to hear from all of you. So if you're interested, reach out to me. In a little bit, I'll also post a link to our homepage, so you'll be able to sort of sign up for future talks. You can register for or kind of sign up for our listserv, and that's a good place to get frequent pokes, frequent reminders to register, and about upcoming talks and just things going on with the seminar series. So I'll post that in a little bit, but for now, let me go ahead and introduce the speaker. So Dr. Tanguy Bertrand received his PhD from the Pierre and Marie Curie University using a general circulation model, or GCM, to study Pluto's atmosphere and surface ice. He then became a postdoc at NASA Ames in the Mars Climate Modeling Group, implementing new numerical methods for Mars climate models, and was also involved in some climate modeling of Triton's and Pluto's atmospheres. Dr. Bertrand is now a planetary scientist working at the Laboratory of Space Studies and Instrumentation in Astrophysics, or LISIA, at the Paris Observatory, where he investigates the atmospheres and surfaces of Mars, Pluto, and Triton. He is also a member of the Mars 2020 Perseverance and SuperCam team, but today he's actually going to be talking to us about some of the climate modeling that he's done for Triton. So thank you so much for joining us. You've got your slides up there, and I'll go ahead and let you take it away. And for folks willing to ask questions, you can use the chat. You can wait until the end, use the raise hand feature and the unmute button, however you'd like to get your questions across. So go ahead and get started.
Thank you very much. Thank you everybody for joining us to the journey to Triton. Sorry in advance for my French accent. I'll do my best. And so today I'm going to talk about volatile transport and climate modeling on Triton, and we will compare as well to Pluto and to what we learned with New Horizons and with modeling on Pluto. And you will see that it is very relevant because both objects have a lot in common. Before I start, I want to mention that a large part of the material of this presentation comes from a paper that has been published in Icarus this year, 2022. So more details are in this paper regarding the observation and the modeling on Triton. So let's start with some observations that are relevant to volatile transport on Triton. So Triton, very quickly, here you have an image of Triton as seen by Voyager 2 during the flyby. It is very bright, and it is very young as well. Very few craters has been observed on the surface. And you can see when you compare it with Pluto that it doesn't contain this very dark region that is called Cthulhu on Pluto. So there is nothing similar on Triton. Triton also has a blue fringe near the equator here that may be nitrogen or methane frost. This is still a mystery. And of course, the difficulty with Triton is that we don't have the exact composition of the different terrains you see here, because Voyager 2 didn't have a near-infrared spectrometer. But we do have Earth-based observations, so we know that there is nitrogen mixed with CO and methane, which are volatile ice. And we know that there is a bedrock made of CO2 and water ice. And basically, we think that the southern hemisphere, you can see here, is made of nitrogen ice cap mixed with methane and CO, maybe with some small grains of CO2 on top of it. And the rest, the northern hemisphere, is made of water ice and CO2 ice with maybe 2–3% of methane-rich ice. So we also have stellar occultations. Stellar occultations data on Pluto have been a golden mine to understand Pluto, and so we do have some for Triton 2. So there is an excellent paper by Joanna Marques Oliveira this year as well, in which she reports surface pressure of 1.4 Pascal for 2017, and she also performed a reanalysis of the previous occultations. So we can, from this paper, we can see here the evolution of surface pressure over time. And we think that the surface pressure have increased in the 90s and then decreased since 2000 to reach, again, 1.4 Pascal in 2017. So finally, there is also atmospheric spectroscopy from Earth-based observations, where we can retrieve the abundances of methane and CO in the atmosphere. So it's a little bit complicated, but basically the methane mixing ratio has increased by a factor of 2 to 4 between 1989 and 2009. This means that it probably requires methane-rich deposits on Triton's surface over a small area. Regarding the CO, it's even more complicated because Lelouch et al. Reported an atmospheric mixing ratio of 0.15%, whereas in 2017, Gurwell et al. Report a mixing ratio which is 10 times less with ALMA. And this is, so both observations may be inconsistent, and it's still a mystery, so the reasons for that remain to be understood. So more detail about this in our paper. And here you can see an illustration of the beautiful spectra here by Lelouch et al. Discovering the abundances of CO on Triton. So we know that Triton shares many similarities with its sibling Pluto. Pluto and Triton have the same size, the same density, the same ices that are non-volatile and volatile. There is very little incoming solar flux. So it's about one of the order of 1 watt per square meter on Pluto and on Triton, at least in 2015 for Pluto, which is, of course, very eccentric. So because of that, the surface temperature are very cold, of the order of 40, 50 K. And because it's all very cold, the processes at the surface of both objects are very slow. They also have the same surface pressure of the order of 1 Pascal. Of course, this evolves with time. Maybe in an opposite season, it will be of the order of millipascal. And they also have more or less the same atmospheric composition, nitrogen with traces of methane and CO. And probably haze, and also haze and hydrocarbons as well. So because of all that, an important message here is that Pluto and Tritons are a distinct class of objects that we can summarize with this sentence. They are cold bodies with a tenuous, condensable nitrogen atmosphere. So because of these similarities, it makes sense that Triton behaves similar to Pluto sometimes. For instance, on Pluto, despite the cold temperatures, the surface remains very active thanks to the ice volatility. And we learned that with New Horizons mission and with the modeling. We've seen that on Pluto, you have cycle of sublimation and condensation, glacial flow of nitrogen ice, erosion of water ice, and so on. The ice distribution is strongly impacted by topography locally. On Pluto, we see that nitrogen ice is in topographic depressions due to the higher surface pressure and the stronger thermal cooling, whereas the methane ice is on high elevated terrains, mostly in the equatorial regions, due to either a low altitude methane-rich atmospheric layer, or it has been also mentioned penitent effects, or maybe it's both sublimation and condensation effects. On Pluto, we also see a lot of different ice mixtures, and there is a departure from equilibrium as well that has been highlighted. And the surface activity may be globally or locally impacted by the albedo feedback, complex evolution of the ice mixtures, mechanisms of stratifications, and we can also think of cryovolcanisms, glacial flow, haze photochemistry, surface contamination, and direct volatile irradiation at the surface. Of all these processes can impact Pluto's surface, Pluto's volatile cycle, and it is likely that it can happen on Triton too. So, but Triton still had its own issues, and it's now fundamentally distinct from Pluto. So what are the main differences? First, Triton and Pluto may have been separated at birth because we think that Triton is a captured Kuiper belt object, as it has a retrograde and highly inclined orbit around Neptune. So because of that, it has complex seasons and possibly strong obliquity tides. And there is also subsequent resurfacing processes, such as cryovolcanism, for instance. So this will lead, for instance, to the geologically young surface without much crater on it, and the globally high albedo, as I mentioned before, no low albedo red areas as Cthulhu and Pluto. It could also lead to the extremely flat terrain that we see on Triton versus a dramatic topography of Pluto, where we see 4 to 5 kilometer tall mountains on the surface. Triton also has active geysers, which may be related to a subsurface ocean. It also has CO2 ice, which has not been detected on Pluto, and a lower amount of atmospheric methane and colder temperature in the lower atmosphere. Both processes could be actually related to the fact that you have much less methane in the ice on Triton. So with that, what are the main science questions related to volatile transport and climate on Triton? So a few questions are, does Triton have a North Polar Cap hidden in the polar night, for instance? If yes, is it thick, is it stable? Why is it smaller than the South Polar Cap? Another question is, how do seasonal cycles affect the volatile ice surface distribution? What are the temporal and spatial scales? Where are the perennial and seasonal reservoirs? And what are the condensation sublimation rates? What are the properties of the volatile ice, such as albedo, emissivity, thermal inertia, and so on? We can also ask what the surface pressure is and how it evolves over time, and the same for the CO and methane gas abundances. And we can also investigate whereas Triton atmosphere collapse, or if at some point it becomes a non-global, for instance. Another mystery on Triton is the fact that the near-infrared rotational light curves seen with IRTF, they suggest that the latitude south of 60 degrees south, so basically the South Pole, are bare of nitrogen, so they don't have nitrogen ice on it. And if this is the case, what could explain that? So that's another question. And finally, regarding the atmosphere dynamics, what is the general circulation regime on Triton, and what controls the thermal profile? So to try to answer all these questions, we developed a global climate model at the Laboratoire de Météorologie Dynamique, LMD. So a GCM contains a dynamical core, so to compute the fluid dynamics equations, so the large-scale atmospheric motions, and a physical core, physical packages, to compute the detail of the local climate. So basically, with such a tool, we can simulate the atmosphere of Pluto and the ice and the evolution of the ices minute after minute with atmospheric circulation and so on. So the GCM has been used on Earth for all climate science. They have been adapted to Mars, Titan, Venus, everybody actually with an atmosphere on it. And it has been recently applied to Pluto. And we can use that same model now to Triton. So what physics does the GCM contain? So here you have the schematics that summarize all that. From the top of the atmosphere, you have methane photolysis with haze formation and evolution. Then you can do radiative transfer through methane and CO and through hydrocarbons and the haze, taking into account non-thermal equilibrium processes. You can have condensation in the atmosphere of nitrogen, methane, and CO. Then at the surface, you take into account the interaction between the atmosphere and the surface, turbulence, convection. The model also takes into account the sublimation, the condensation, of course, of the volatile ice. And you can have a glacial flow model, make different mixtures of ice on the surface. And then in the subsurface, you can have an internal heat flux and you compute the equations of subsurface conductions. So this model can do a good job at simulating Pluto. And in fact, we also have a reduced version of the GCM, which is called the Volatile Transport Model. And it's a reduced version because we parameterize the atmosphere and the transport of the volatile nitrogen, CO, and methane. And we can do that removing the atmospheric processes because Pluto and Triton atmosphere are very tenuous, and so they do not impact the thermal surface balance. So with this reduced model version, and you see here what processes are left in that reduced version, we can do a good job at computing the volatile cycles to first order and very quickly, which allow us to simulate the volatile cycles over seasonal and astronomical timescale. So a first investigation with the models is the following. Pluto and Triton were originally twins, but may differ now because of their obliquity, question mark. So here you can see on the left, the obliquity of Pluto over time. So the obliquity changes from 53 degrees to 76 degrees in retrograde rotations, okay? So basically, it corresponds to a mean obliquity value of 65 degrees, so rather a high obliquity. Whereas on Triton, on the right here, you can see the evolution of the subsolar point with time, and you see it's very chaotic, but it can be extrapolated over the last 10 million years. And if we do the average of the obliquity here, we find a value of 30 degrees, so it's rather low obliquity. So this difference in obliquity between Pluto and Triton reflects in surface temperatures. Here you can see the mean surface temperature of the bedrock on Pluto on the left and Triton on the right. And over the last obliquity cycles on Pluto, you see that the poles are much warmer than the equator, whereas on Triton, the equator is much warmer than the poles by 5 Kelvin in average. So this difference is already striking between both bodies. The fact that the ices may want to go to the equator on Pluto because it's colder there, and on Triton, it may want to go to the poles. So to test the impact of obliquity on the volatile cycle, we performed an experiment with the model. So here you have Pluto on the left and Triton on the right. And we have an initial state of the model, which is all ices homogeneously distributed with 200 meters of nitrogen ice and 4 meters of methane ice. This is why the map is blue right now. And then we run over 20 million years with the same model, same parameter, and same initial state. The only difference is that we compute Pluto with its orbit and obliquity and topography, and the same on Triton, we assume that its topography is flat, but it has its own orbit and obliquity. So when we run the animation, we can see on the right that after 1 million years, the ice is already at the poles with a little bit of frost of methane-rich ice, whereas on the left, on Pluto, the nitrogen ice migrated to the equatorial regions and inside the Sputnik planitia, and you have methane frost at the poles. And if you wait more time, more nitrogen ice will fill Sputnik planitia, and you are left with some thick methane deposits at the equatorial region as well. So now we can repeat this simulation with some changes. So now on the left, we run a simulation of Pluto, but with the orbit of Triton around the sun. So basically, it corresponds to a change of eccentricity of Pluto, the eccentricity of Neptune here, so 0.009. And on the right, it's a simulation of Pluto, but now with Triton's obliquity, so with the chaotic variation of subsolar point, and we don't touch the eccentricity of Pluto. It remains the eccentricity of Pluto in this one. So what happens if we run these simulations? So on the left, you see that we are still seeing Pluto with the ice in the equatorial regions and filling Sputnik planitia. So changing the eccentricity didn't impact much the face of Pluto. Whereas on the right, changing the obliquity of Pluto and switching to a Triton obliquity type really affected the distribution of the nitrogen ice, and the ice migrated to the poles and a little bit in Sputnik because the ice is actually flowing into this big, deep basin. So basically, we see here that Pluto looks like Triton if you use a Triton obliquity. So what we can say here is that we reproduced Pluto and Triton ice distribution from the same model to the first order. And this supports the fact that both objects had a common origin, but then they evolve differently because of their orbit and obliquity, and the fact that Triton had this heavy capture. And in fact, it's overall the obliquities that controls that. The obliquity completely changes the face of the planet. If you have a high obliquity equivalent, then the ice go to the equatorial regions, as on Pluto. If you have a low obliquity equivalent, then the ice migrate at the poles, as on Triton. And of course, it's interesting because the impact of obliquity can go beyond the ice distribution, because if you have the ice at the poles, this may prevent the formation of methane-rich deposits, as we will see later. And this may have an impact on atmospheric temperatures because you have less methane in the atmosphere, an impact of photochemistry and haze formation and escape and many aspects of the climate. So the entire atmosphere is impacted by the obliquity. So let's get back to the simulations of volatile cycle on Triton. So as you could see on the animation, the nitrogen ice accumulate at the poles, and then you have symmetric permanent polar caps if the surface properties are uniform. The cap extents depend on the nitrogen reservoir, the timescale for glacial flow, and so on. However, Voyager 2 saw that the southern cap was more extended in 1989. So what could explain a north to south asymmetry in the caps of nitrogen ice? So it has been shown that it could be due to internal heat flow or to a nitrogen ice albedo difference with a subsequent positive albedo feedback. So this scenario has a name. It's hard to pronounce. It's called Koyanis-Muyo. And of course, the albedo difference may be triggered by different processes, such as contamination of the ice by dark material, the effect of sensible heat flux, or the phase transition between the alpha and beta phase of the ice, and maybe other processes as well. So we explored that a little bit in our paper again, but this time with our model. And we found that, yes, it works. We can obtain an asymmetry in nitrogen ice between the north and the south on Triton. So here, in this figure, latitude versus time, you see that we start at a time equal to 0 with an initial state of global coverage of nitrogen ice. And after 1 million years, you see that the cap at the south is more extended than the cap at the northern hemisphere because we used an albedo difference between both. So we end up with two asymmetric polar caps on Triton that are very stable. So now the idea of the paper that we published was to explore the sensitivity of the volatile cycle to the main model parameters, such as the bedrock albedo, the soil thermal inertia, the initial reservoir of nitrogen ice, and the internal heat flux. So we performed a lot of simulations, varying all these parameters, and we obtained a zoo of simulation results that's with a lot of complicated figures that I will not detail, but instead we will go to the main results. So the idea is to take all these simulations and to look for the best case simulations that match our list of observable. So for instance, the fact that we have a surface pressure of 1.4 Pascal in 1989 and 2017, the ratio of volatile, non-volatile fractional area, the albedo of the surface, the temperature as well must be consistent with what has been seen by Voyager 2 and the IRIS instrument. And we also want a bright southern cap made of nitrogen ice extending to at least 30 degrees south. And the northern cap that doesn't show up in 1989 below 45 degrees north. So we take all that and we try to extract the best case simulation. So here is an example of a simulation that match most of the observational constraints. So you can see it's a latitude versus time figure. The colors correspond to the sublimation condensation rates. So in red, this is where nitrogen condenses, and in blue, this is where nitrogen sublimates. The gray line shows the evolution of subsolar points. So this is basically summer in the northern hemisphere, and this is here summer in the southern hemisphere. And the red line shows the evolution of surface pressure. So you see on the right y-axis here that we have 1.4 Pascal in 1989 and about 1.4 Pascal in 2017 as observed from stellar occultations. So here on this simulation, the model predicts that there is a permanent and small northern cap here, and here seasonal frosts that extend down to 45 degrees north around 2020. You see, we also have access to the sublimation and condensation rates, and they are of the same order of magnitude than the sublimation condensation rates on Pluto in Sputnik Planitia. They are up to 0.5 millimeter per day, per Pluto day or per Triton day. So results was about the nitrogen ice thickness. So it turns out that all our best case simulations were obtained with a relatively large reservoir of nitrogen ice. So we expect that the southern cap of nitrogen to be at least 100 meter thick, maybe 1 kilometer thick at the South Pole. And it is, of course, balanced by glacial flow. And this is consistent somewhat with images from Voyager 2. Here you have this figure that shows the macular southern terrains near the equatorial regions. And you see the topographic barrier between the cap and the bedrock, probably. And it is consistent with maybe here a boundary of 100 meters to several 100 meters in height. So we also extract from our simulation the surface pressure. So here you have a figure showing the surface pressure versus time for different class of simulations. So basically the blue lines are class number 3, mean that they match all our observational constraints. And you see that you can reproduce the increase of surface pressure in the 90s. We reach a peak in 2005 and then a decrease after that. And so what we can say is that we have similar pressure variations than on Pluto, so with variation of 2 orders of magnitude. We can say it's difficult to match the strong surge of pressure reported in the 90s. So this corresponds to the peak here. So we don't have much, we actually don't have simulations that go as high. We can say that the pressure is expected to decrease in the next decades, but remain over 0.5 Pascal. And there have been an occultation of Triton on October 6th, so it's very recent. It remains to be analyzed, and Bruno Sicardi already told us just before this talk that we have data, it has been successful. So this is very good news. We also simulated what happens with CO and methane cycle. So regarding CO, CO is well mixed in nitrogen, and in our simulation, we obtain a CO ice mixing ratio. We have a CO ice mixing ratio of 0.4%, and it gives us a mixing ratio in the atmosphere of 0.006%, which is consistent with the observation of ALMA. Regarding methane, we don't form a methane-rich deposit in the model. This is unlike on Pluto. And the methane cycle is very sensitive, of course, to the model parameters. So here the figure shows you the methane partial pressure in a nanobar obtained in some simulations where we actually place methane-rich ice at the cap edge. So these are the solid lines. In this case, the partial pressure remains constant during this season. And if we place methane-rich ice at the South Pole, then it follows an evolution a little bit like the nitrogen pressure, with an increase until year 2005 and then a decrease. So this shows that it's very sensitive to the model assumption. So this is actually a question. So why we don't see large-scale methane-rich deposits on Triton? Because on Pluto, we see the bladed terrains in the equatorial region, and on Triton, we don't see anything like this. It may be because the global reservoir of methane ice is too small on Triton. It may be because we don't have enough topographic gradients, and in the end, methane is under the nitrogen or mixed with nitrogen. It may be because at the poles, the coldest area are too small, And you need more topographic gradients in this area to form both nitrogen-rich and methane-rich deposits. So it's still a question that remains to be fully answered. We do see some funny-looking terrains on Triton at the cap edge with an alternance of dark and bright regions. So here you see, for instance, a dark area on the image on the right, near the equator. And this dark area may be a concentration of ice deposits. They may be similar to the dark plains north of Sputnik Planitia. And they may be also they may contain methane-rich ice that will actually be consistent with the IRTF observations, which show a peak of methane absorption near this longitude for the period of 2002-2014. So that may be where the methane-rich ice is hiding on Triton. Regarding the blue fringe at the equator, we actually don't know if it's nitrogen-rich frost. Maybe it will be consistent with some model results showing that nitrogen condense actually in the equatorial regions. It may be consistent with IRTF as well in this case. It may be methane-rich frost. That will also be consistent with the fact that in the model we do see some methane-rich ice near the cap edge, but it will not be consistent with the IRTF observations, and it will not be consistent with the fact that usually once nitrogen sublime and reveal methane-rich ice, the ice is relatively dark. And here, this may rather corresponds to bright, fresh frost. So to conclude on this region, we should keep in mind that albedo and composition, positive feedback may also be efficient to increase the local contrast in ice sublimation and condensation rates. And so here you see on Triton, we have a transition between bright and dark terrains, and this may be an evidence of positive albedo or composition feedback. And on Pluto, actually, we suggested albedo feedback to explain the difference between bright and dark regions here in Sputnik Planitia. So I don't know if there is much time left, but I will try to accelerate a little bit and talk about atmosphere dynamics on Triton. So first, a little bit of fundamentals and what we learned from Horizons and Pluto modeling. So we learned that on Pluto, so this cold and the tenuous condensable atmosphere of nitrogen is tenuous and transparent. So we know that atmospheric processes such as clouds, haze, and so on have no significant impact on the relative thermal balance at the surface. We learned that the near surface circulation is dominated by katabatic winds, so downslope, superimposed on sublimation flow. So nitrogen sublimes and condense. So you have a flow from the subliming nitrogen ice to the condensing deposits, associated as well with the Coriolis turning of the winds. So you can find that in the paper by Forge et al. Or Bertrand et al. 2020. We also learned that the general circulation is mainly driven by the condensation and sublimation flux, not necessarily by the thermal contrast in the atmosphere. And the consequence of that is that the general circulation is strongly sensitive to the distribution and the seasonal evolution of surface nitrogen ice reservoirs. So it's really where the nitrogen ice is on the surface that controls the flux, and therefore that controls the general circulation. We looked at several scenarios for Pluto, and we think that the regime is dominated by a retro-rotation. I will come back to that. And we also, with the model, highlighted the fact that the atmosphere can contain tides, gravity waves, and barotropic waves. And there is also a debate. The radiative timescale of the atmosphere may be 10 Earth years, or maybe much less, for instance, 1 Earth year, if the haze have a strong radiative effect. So this is also debated. So all of this process of these fundamentals of Pluto's atmosphere and Pluto's dynamics may also apply on Triton. In fact, on Triton, we have a little bit of observations that are relevant to the circulation, the atmospheric dynamics. It's the fact that at the South Pole, we do see surface wind streaks that are oriented towards the east, so that are retrograde, and altitude plumes here with the blue arrow that are oriented to the other direction, so northwest, they are prograde. So you see here on this schematics, we have prograde plumes and retrograde wind streaks. So this is an indication of the wind direction at the surface and at 8-kilometer altitude in 1989. So we can use our GCM that models the winds and try to find a scenario that will be consistent with this wind direction. So very quickly, on the left, you have a simulation with a northern polar cap. And you see that if we place a northern polar cap, then the surface wind blow eastward. So this is consistent with the observation. And when we look at the zonal mean, zonal winds in 1989, we obtain here a retro-rotation because you see that the winds are negative, so to opposite direction of the rotation of the surface. And but we do see a prograde jet in the first 10 kilometers that will be consistent with the prograde direction of the plumes. Whereas if we run without a northern polar cap, interestingly, we still have prograde winds in the atmosphere here above the south polar cap, but the surface winds blow westwards in this case, so they are not consistent with the observations. So maybe maybe here we need a north polar cap to be consistent with the wind direction observed by Voyager 2. So very quickly on Pluto, we have a meridional circulation with nitrogen ice subliming in the northern hemisphere and condensing in the southern hemisphere. So by crossing the hemisphere, by moving from one hemisphere to another, the nitrogen molecule slow down by conservation of angular momentum, and so it leads to a retro-rotation. And actually on Triton, if you have a condensation of nitrogen in the north polar cap, you will have the same phenomena. The nitrogen molecule move away from the rotation axis as they cross one hemisphere to another, and so they slow down, and this leads to a retro-rotation of the winds here. And we do see in both cases some prograde jets in the first 10-kilometer altitude. So there are different conclusions. Conclusions for Triton itself is the fact that we do form polar caps at the poles. They extend to low latitudes through glacial flow and through the formation of thinner seasonal deposits. You can have then asymmetries in surface properties to favor the development of one cap over the other. According to our models, we believe that a small permanent north polar cap should form on Triton and should exist, should be present. The northern cap actually and warm equatorial latitudes are sufficient to explain the wind streaks and the plumes direction observed in 1989. Regarding CO, CO is always trapped in nitrogen ice and is consistent with the ALMA observation. Methane-rich deposits on Triton may form at the edges of the cap once the seasonal nitrogen deposits have entirely sublimed. And regarding the surface pressure, this is consistent with the observation, except that the dramatic increase in surface pressure reported in the 90s is difficult to match. And we expect the surface pressure to decrease in the next decades. And we will test this model prediction with a recently and successful stellar occultation acquired on Triton last week. Another conclusion is the fact that Pluto and Triton are a distinct class of object of planetary climate. They are cold bodies with a tenuous condensable nitrogen atmosphere. And if we look at what are their place in the solar system, we can make this conclusion. So Pluto and Triton have a rotation regime which is intermediate. It's not a fast rotator like the Earth and Mars. It's not a slow rotator like Venus and Titan. It's intermediate. And maybe because of that, on Venus, you have a super rotation on Titan 2, whereas on Earth and Mars, you have westerlies and trade winds. Well, on Triton and Pluto, you have a retro-rotation because of nitrogen ice moving from one hemisphere to another. On Triton and Pluto, you also have nitrogen as a dominant gas, just like Titan on Earth. And the dominant gas condensed, like CO2 on Mars. You have clouds, maybe of methane, of hydrocarbons, like in many other planetary climates, and an atmospheric haze, organic, like on Titan. Another conclusion is that Pluto and Triton may have a common origin, and this is strongly supported by our simulations. We see many common points. Pressure variations are similar, no atmosphere collapse, the condensation rates are similar, glacial flow, sensitivity to albedo feedback may occur on both bodies. We find with our simulations that they may have a similar reservoir for nitrogen ice, which is above 100 meters in global average. Similar as well thermal inertia, and of course, similar atmospheric dynamic regimes, as I just mentioned. But Pluto and Triton may differ now due to obliquity. Obliquity is high on Pluto and low on Triton. And because of that, on Pluto, nitrogen and methane, they tend to go to the equator. And there is a high sensitivity to topography. And you may have a large and permanent methane-rich deposit, whereas on Triton, it's hard to find large methane-rich deposits. And since Triton is very flat, the sensitivity to topography is much lower. And of course, this impact of the obliquity goes beyond the ice distribution, as I said, and this is the key message, is that the obliquity impacts everything from the formation of methane-rich deposits to the atmosphere temperature, photochemistry, haze formation, and escape. And I think this is my last slide. So I thank you very much. And I take a question if you have some.
Awesome. Thank you so much. Yeah, I think, I can see some like clapping icons in the audience. This is really exciting stuff. I really liked that chart that you had a couple slides ago that sort of, had this comparative planetology across. For a lot of us, myself included, it can be so easy to just kind of focus on one object at a time. And sometimes I feel like you can get tunnel vision that way, but definitely starting to compare things across the solar system. And you have a background with Mars, so it's probably, particularly easy for you to kind of have that mindset. So it's really great to see that. And so if folks have any questions, feel free to put it in the chat. You can also raise your hand, use the raise hand feature that I think is at the bottom of the Zoom screen. You can unmute yourself, or if you'd like me to ask your question for you, you can put it in the chat. So I'll start out with a question. So I'm always really excited about missions, looking forward to future missions. So I'm curious, in your mind, is there any spacecraft data, maybe in addition to the images that we already have from Voyager, from a flyby, an orbiter, maybe even an in situ lander that could, sort of provide some information to help validate some of the predictions that come from these models?
Of course, it would be great to have a flyby or an orbiter and have some spectrometers on board and maybe map the different composition of the ices on Triton. As I mentioned during my talk, there are a lot of hypotheses for the blue fringe, for the dark regions, for the cap itself. And of course, if we could just map all that with a near-infrared spectrometer, we will have a lot of answers. I think then having all these instruments will help to compare the different ice mixtures and with Pluto, and we will try to understand how these ices behave on both subjects. And there may be many other instruments that we could carry on to Triton, and actually to Triton or to Pluto as well, to complement the observation we have. But also we should keep in mind that we can do a lot of science with Earth-based observations, and in particular, I didn't mention, but we will observe Triton with James Webb. There is a GTO for that, and in fact, in our paper, we provide some examples of what we can do with James Webb. And although we don't have the spatial resolution, we can still learn a lot about the atmosphere itself, how the haze impact the temperatures, or how the what are the properties of the surface, and so on. And I think this is very important to understand all these objects that are in the Kuiper belt that share similar properties.
Very cool. Thank you. Yeah, I think I saw Candy had her hand up first. So yeah, go ahead, Candy.
Oh, I think this was a great talk. I really enjoyed it.
Thank you.
I don't actually have a question. I just wanted to comment that I was really struck by the fact that your modeling of the atmospheric circulation leads to the necessity of having a North Polar cap. I hadn't really ever seen that conclusion before, or the work leading to that conclusion before. So thank you for that.
Yeah, so I can comment on that. Just the fact that we still have a lot of analysis to do regarding the circulation. And here I just provided 2 examples with a North Polar cap and without a North Polar cap. But for instance, I didn't analyze the results if we have another extent for the North Polar cap, or I didn't actually look at the sensitivity of the model parameters. Just 2 examples with and without the North Polar cap. There may be other scenarios that can explain the prograde plumes and the retrograde wind streaks. Just to let you know.
All right, yeah, I think Heidi, you had your hand up. Go ahead.
Yeah, that answer leads right into my question. First, I'm very happy that the JWST data, the spectroscopy that is going to come in, is going to be fabulous. And I'm glad to hear you guys are really looking forward to that. My question was about that very topic you were just talking about. I missed your explanation of how the North Polar cap did make the plumes go one direct, the plumes of the active cryovolcanism go one direction, but I didn't understand how it went. The ground surface ones went the other direction. Did I miss something there, or is that?
No, I didn't explain it in detail. The reason is that it's still an analysis that remains to be done. The full analysis of the circulation has not been done yet, so I cannot say much. But I can say that so you have a circulation cell which is open with the sublimation of nitrogen in the south and condensation in the north. And of course, you have a deviation by the Coriolis force, so that explains part of the winds near the surface. But you also have an effect of a little effect near the cap edge of thermal winds, because the equatorial belt is warm; it has no natural ice in it. So you may have an effect of that. So all the effects of the different components of the circulation must be analyzed, and so it has not been done yet. So I don't know yet exactly what controls all the circulation.
Great. Oh, thanks. So sounds like we need a mission.
Yeah, definitely.
Thank you.
All right. Any other questions? You can post them in the chat or use the raise hand feature. If it's all right, I'm going to ask another question. So at the beginning, or toward the beginning, there was this chart that you had that showed the differences between the obliquity of Pluto and Triton. And of course, Triton's was kind of all over the place. There were a few, waves kind of contributing to its obliquity cycle. So I don't know a ton about these 2 systems, but I'm curious what the cause of that actually is. And I'm sure it's something simple, and I just don't know what the answer is. But yeah, what's the cause of this?
Okay, so short answer is perturbations by planets on Pluto. And for Triton, of course, it has a retrograde orbit, plus it is not exactly in the same plane as the other moons of Neptune. And all of that lead to this chaotic evolution of the subsolar point, the fact that you have the precession of Neptune and so on. So it's a complex combination of all of this that leads to these differences.
Okay, thank you. Yeah, Leslie, I just saw your hand go up.
Thanks. Absolutely fantastic talk, Tanguy, as expected.
Hi, Leslie, thank you.
I'm just putting in here, in case anybody missed it at DPS, there's a new Frey and Schmidt style paper compiling a lot of the vapor pressures and ice densities and things, like a lot of the ices that we love, if you are the kind of person that comes to a talk like this. So I'm going to throw that in the chat.
Great, thank you. I haven't been to DPS, so I'm very glad you share this.
It was wonderful. I'm sure that we're all still recuperating from it. It was an incredible conference, tons of information, but I'm sure we're all exhausted from it. I'm exhausted. Okay, yeah. Any other questions? Thanks, Leslie, for posting that in the chat. Try to give a break in my speaking to let people come up with questions. If there aren't any other questions, then usually we have this sort of slide that I put up, community news, just to make sure that the Ice Giants community is still talking and you know, making sure everyone knows what's going on in the community and you know, keeping things moving in the community. So if it's all right, I'll flash that slide up and it'll just sort of be a quick, let's see.
Yeah, and if we're done with the talk now,
yeah.
I have a little commercial.
Sure.
Yeah. You know, we were talking about missions to Triton, and the New Frontiers 5 draft AO is out for comment right now. And a couple other people and I have been working on a letter to Kurt Niebuhr saying that actually the Triton mission that was recommended by the new decadal survey, but recommended for New Frontiers 7, should be added to the New Frontiers 5 list and not go through a CAPS process, but solely based on the scientific rationale in the decadal survey. Mm-hmm. So not to delay, because this was the big concern at OPEG, was that adding a mission to New Frontiers 5 would delay the call. And so the letter is very, very clear about don't do this if it delays the call, but you don't probably need to go through CAPS. And so I'll be sending out an email, hopefully today, actually, if people want to endorse the sentiments of that letter, there'll be a place to add your name.
Okay, great. Yeah, if you want to send it out through the Ice Giant listserv, I think you can just send it to the email address that you get those emails from, and it should go through to the entire listserv if you'd like.
Okay,
would be great.
Wonderful.
Yeah, thank you. Yeah, that would be excellent.
Get that mission sooner rather than later.
Definitely. I agree. I'm sure we all agree. I would love to see that.
Especially after this inspiring talk.
Yes, right. Exactly. Yeah, so in addition to that, here, I'll copy paste these into the chat, because I know whenever there's links on a slide, you're like, I can't click on those. So let me paste this kind of ugly block of text in there. But like Candy mentioned, that right, the New Frontiers 5 draft AO to be released soon. And then a special plug for next month's Ice Giant System seminar series. It'll be Will Saunders. We'll be talking about Uranus's atmosphere. And of course, if you ever have anything that you would like to advertise through this, like I said to Candy, you can plug it through the listserv. You can send an email to the listserv, and I'll approve it, and it'll send out to everybody. I think there's almost 250 people subscribed to the listserv, so you'll hit a good chunk of the community. And you can send me things on this community news, to be put on this community news slide, so that everyone at the meeting will kind of see that. Yeah, Leslie, what's up? Oh, wait, you're muted. Sorry.
Oh, sorry. As long as we're doing community news,
sure.
AAS abstracts are due today at midnight. I forget which time zone. And the ICEs in the solar system, which is the same week as AAS, those abstracts are due next week. but registration is filling up. So I tossed the link into that as well.
Okay, ICE is in the solar system. Is it a hybrid meeting? I feel like I've heard of it.
I do not know their hybrid intentions. I assume it's hard not to have a hybrid aspect to a meeting these days. But as COSPAR taught us, the hybrid can absolutely stink.
Okay, sure. Okay, it might be in person in Canada, Montreal. Okay, in January. Gotcha. Okay, awesome. Yeah, thank you. Yeah, and definitely, if anyone has anything to plug, you can go ahead and throw it into the chat. If there are no other things, then we can go ahead and close this out. And thank you again, Tanguy, for this incredible presentation. It sparked a lot of good conversation, and I'm excited for what's to come. Hopefully we'll get a mission out there, like Candy said. Hopefully we'll get some, some good James Webb observations. And yeah, I'm stoked to see where this field goes. It's really exciting stuff.
Well, thank you to everybody as well, and thank you for inviting me to talk to the seminar series.
Absolutely. All right, I'll go ahead and close this meeting out. Thank you all so much.
Bye, everybody.
Bye-bye.